Okay, good evening, everybody. We're going to pick up now with where we left off earlier, which is talking about why there are two major types of planets. Just to quickly recap, we were looking at the nebular hypothesis and trying to make sense of why a planetary system has different kinds of planets, why there are asteroids and comets, why the orbit of why there's an orderly motion to celestial bodies in a planetary system, and also somehow we need to be able to explain the fact that there are exceptions to these rules. So to start, we're going to talk about why there are different kinds of planets. And again, there are two major categories. We have terrestrial planets. Those are the small rocky planets like Earth, Mars, Mercury, and Venus. And then you have Jovian planets, planets that are gas giants. They are Jupiter-like. For example, Jupiter, Saturn, Uranus, Neptune are all gas giants. The emphasis should be the fact that they are hydrogen rich, right? They have a lot of hydrogen. So if we look at the different objects in our solar system, if we look at the different materials specifically, we took all the different objects in our solar system, we collected them into a giant pool, and then we split them up into individual atoms. And we said, okay, what atoms do we see the most of in our solar system, and what atoms do we see the least of? And what we see is a solar system that is mostly hydrogen and helium gas. Remember that our sun, the star that we orbit, is mostly hydrogen and helium. And again, it's 98% of the total solar system's mass. In this chart, there's a column there that says typical condensation temperature. Does anybody know what that means? What is condensation?
Condensation is when, like, I believe evaporated water becomes like not like a solid, but like cold and starts to fall back down.
Like a liquid.
Yeah.
All right. Okay. You could even go ahead and say it could condensate into a solid. But that was actually a very specific example, because you said that it sounded like you were saying it strictly has to do with liquid water or water. But condensation is, any element can condensate from a gas into liquid or solid. And there are temperatures at which that occurs, right? Different temperatures depending on the material. So like water will condensate at 212 degrees Fahrenheit. It'll go from a gas into a liquid. But a metal will condensate at a much higher temperature. And metals can condensate, thousands of degrees. Right, and so I think what would be the opposite of condensation? I think you actually kind of said it, Aman.
Accumulation?
Not accumulation.
Precipitation?
Mm-mm.
Evaporation?
There it is. Evaporation is the opposite of condensation. So think about it like, so the evaporation temperature and the condensation temperature are the same. It's just whether you're approaching that temperature from the hotter side or whether you're approaching it from the colder side, right? If you're approaching it from the colder side, then when you get to that temperature, the object's going to evaporate. But if you have a gas and you're approaching that from the hotter side and you cross into the cold, then it's becoming a liquid, right? That's condensation. So evaporation is one way, condensation is the other, but the temperatures that turning point is the same, or that critical temperature is the same. So another way to think about that would be to say, like, water melts at a lower temperature than metal. That makes sense, right? That's like pretty easy to understand. For some reason, that I think that just works better for a lot of people. Okay, so the typical condensation temperature. Hydrogen and helium do not condensate. They stay in a gaseous form. They do not condensate into a solid. Hydrogen compounds, water, methane, ammonia, they do condensate once the temperature gets below 150 Kelvin, which is pretty cold. Okay. Hydrogen compounds are molecules in which hydrogen has mixed or combined with something else. All right, so H2O, methane, ammonia. Then we have rocks, right? Rocks are made up of various minerals, silicates, lots of oxygens, potassiums, whatever, which has a higher condensation temperature. In other words, it has a higher melting point. So, you could be at, I'm looking at the temperature, the typical condensation temperature ranges there. And I don't know, let's say that we had 350 Kelvin, right? At 350 Kelvin, you're right between the rock and hydrogen compound condensation temperatures. At 300 Kelvin, you would have hydrogen compound that's still a gas, but rock that is now a solid. If you went above 500 Kelvin, you'd start melting some rocks, right? You'd start getting some liquefied rocks or gaseous rocks. And metals too, right? Metals have an even higher condensation temperature or an even higher melting point, right? You got to get metals to a much higher temperature. Now, once you get to rocks and metals, we're talking about less than 1% of all of the solar system's mass. Less than 1% of it is rock and metal, which is crazy if you think about it, because what is Earth if not rock and metal? So let's talk about this. Why are these important? Well, these are the different materials in our nebula, and the typical condensation temperature is actually what's going to affect where you find most of these. So there's a distance from the sun at which point the temperature is freezing, right? So if you are in here, in this region, between the sun and the frost line, it is hot enough to have liquid or gaseous water, but not ice. Once you cross the frost line, now it starts to get cold enough in the solar system for ice to form, right? So it's too warm in here for hydrogen compounds to freeze, but rocks and metals can freeze at these temperatures, right? If you wanted to find gaseous and gaseous rock or metal, you'd have to get much closer to the center where it's much hotter, right? So you only have to go a little bit of a distance before rocks and metals start to condensate. You have to go beyond the frost line before these hydrogen compounds condensate. Okay. So I'm going to pause real fast. Does anybody want to ask anything to clarify what I've said thus far? Moving on. Okay, so we have two types of planets. The frost line plays a big role because the planets that form within the frost line, right between the sun and the frost line, those are going to be your rocky terrestrial planets. Those are the ones made of mostly rock and metal. Beyond the frost line, in the region of the solar system where not only rocks and metals condense, but also hydrogen molecules condense, or hydrogen compounds, right? Now you start to get these icy planets also, right? Big icy planets. Okay, so why is that significant? Well, if we look at this chart again, okay, but just by percentage of mass in the solar system, there are more hydrogen compounds than there are rocks and metals. So the rocks and metals that condensate within the frost line are going to form rocky, metallic planets, but they're not going to be particularly large because the hydrogen compounds are not at a low enough temperature to also condensate and add to the size of that planet. Beyond the frost line, the hydrogen compounds also condensate, right? So like Jupiter, Saturn, Uranus, and Neptune, they have rocks and metals, plenty of rock and metal in them, but they also have hydrogen compounds, which gave those outer planets much more mass. And because they have mass, the gravitational pull of the Jovian planets is stronger than the gravitational pull of a terrestrial planet, right? Jupiter's gravitational pull is much larger than Earth's. So in the early solar system, as hydrogen and helium gas, which do not condensate, or which do not condense at all, as those get pushed out, the outer planets, the Jovian planets, start to accrete hydrogen and helium. And that just adds to their mass. So the Jovian planets are capable of pulling much more matter onto them. And that's why they get so much bigger, right? It's because there are also hydrogen compounds that make up the body of those planets, so they can get massive enough to really hold on to a lot of hydrogen and helium gas. And that's what this last line is, right? The additional ice particles outside the frost line made planets there in that region more massive. And that excess gravity drew in all of the hydrogen and helium gas. Right. So that brings us to asteroids and comets. Right. So in the very beginning, early in the accretion process, right, we start out with all of these clumps. And the clumps become planetesimals. Some are small, some are large. And these planetesimals collide with each other. They're on crisscrossing paths. You can see here that a lot of them crisscross with each other or are very, very close by. And so they crisscross and they collide and they break up and they combine and make even bigger planetesimals. And some of those planetesimals end up growing large enough to become protoplanets, right? Pre-planets. So the largest ones grow, the smallest ones get accreted onto the larger ones. And then after time, right, the planetesimals that survived this era of the accretion process become fully fledged planets. Right? Now, we talked about the distribution of matter, right? How rocks and metals are able to condense within the frost line, but rocks, metals, and hydrogen compounds can condense outside of the frost line. Because ice condenses beyond the frost line, that's where we find most of our comets. Right? Most comets are in the outer solar system, beyond the frost line. within the frost line, that's where you're going to find most asteroids. Asteroids are not particularly icy objects. They are very rocky and metallic. All right, let's see. Where does this link take us? Ah, yes. Okay. So let's take a look here. I may have this come up somewhere else in a future slide, but while it's here, I'll pull it up. All right, so these are, this is the International Astronomical Union. This is a series of animated GIFs about where you're going to find most solar system, most asteroid objects. Right, so you can sort of see here, right? There are 4 blue rings. The sun is in the middle. The innermost ring is Mercury, followed by Venus is this red one. The very, very light blue, you can barely see it there. I'm moving my mouse with it. That's Earth over there. And then out here is Mars. Oh, the GIF restarted. So here's Mars out here on the right. All right. And you can even see here, you know, there's like the orderly motion, right? Everything's going around the sun in the same direction. You can tell here, you can sort of see Kepler's laws at work, that the planet closest to the sun orbits fastest or moves fastest and has the shortest period. And then as you get to Mars, Mars moves a lot slower, right? Just some interesting stuff. So then what are all these other dots? Well, the red dots are asteroids. Right? The red dots are asteroids that are considered near Earth asteroids, near Earth objects that orbit within the inner solar system. Right? So these are the ones that we, you know, are trying to watch out for. Right? This is like when scientists say, you know, what's the chance of an asteroid hitting the Earth? It's these red ones that we care about. The green dots, which are far more plentiful, those are asteroids also. And they are existing in a particular region of the solar system called the asteroid belt. Right, and you can see just the density of these regions, like that, the red near Earth asteroids, not so many, right? But these green ones in the asteroid belt, oh my God, they are innumerable. Right? There are so many of them. Okay, so we've got the near Earth asteroids, we've got the asteroid belt, and there's actually another region of asteroids, but it's really hard to see in this diagram. So I'm just going to zoom in as best I can. If you look in the outer ring, this outer ring represents Jupiter, right? So the asteroid belt is between Mars and Jupiter. If I zoom in over here, do you all see this dot here? That blue dot with the crosshairs? Yeah, kind of, sort of.
Yeah.
Okay. So it's a little bit hard to see. I'm going to keep my mouse on it until the GIF repeats, then I'll move my mouse to wherever Jupiter goes. But if you look along Jupiter's orbit, ahead of Jupiter, right in here, do you see all these blue dots? Oh, okay, hold on. Jupiter's here now on the right side. You see all these blue dots up here? Oh, sorry. Blue dots up there. Here's Jupiter. Well, more blue dots in the middle of the screen now. It's hard to see because it's a dark background, but those are also asteroids that orbit ahead of and behind Jupiter in Jupiter's orbital path. They are called Trojan asteroids, all right? Just like a Trojan horse. And then we've got the outer solar system. Right, and in the outer solar system, there are far fewer objects there. Right, but you can sort of see Now we're like these four rings now represent Jupiter, which is the innermost one, Saturn out here, Uranus, and then Neptune's this really far one. And all of these little red and yellow and gray dots, those are comets. And this is we're looking at the Kuiper belt. Okay, so I'm gonna share a different screen now. So now, I don't know how many of you were watching the lecture earlier where I had my little snafu with the slides. I accidentally pulled this one up before the one I was supposed to. So now we're going to move on and we're going to talk about these different questions. All right, we sort of addressed, characteristics about the different planets. We talked about the difference between terrestrial and Jovian. And we started looking at the early solar system and sort of how solar systems form in the first place. So we're going to talk about the interior structure of the Earth. And I want to start by saying, to follow up on like we talked about how the very early solar system formation, we had the collisions of all those different planetesimals, right? They had crisscrossing paths, the planetesimals were small, they collide, some get bigger, some shatter. The large ones usually accrete the smaller ones and acquire even more mass. And then after a long enough time, after that period lasted long enough, we were left behind with the major planets, or the full-fledged planets. This era, when all of those tiny planetesimals were hitting each other, it's called the era of heavy bombardment. And we're going to come back to we're going to come back to that in a little bit, and why knowing about the heavy bombardment era is useful. Right? Again, it's when those leftover planetesimals, the ones that never fully accreted into planets, struck the almost fully formed planets. It's this era of heavy bombardment. And you can see like the results, you would expect lots of cratering, right? This period of time where just planetesimal after planetesimal bombards the early surface of the planet, just crater after crater. Okay, so to recap, where do asteroids and comets come from? They are the leftovers, right? They are the objects, the planetesimals that never fully made it into a planet, right? And we also talked about the exceptions to the rules for nebular theory. All right, so we might be able to explain like the fact that Earth's moon is so large compared to the size of Earth, the fact that Venus rotates in the opposite direction on its axis compared to all the other planets, the fact that Uranus has such an extreme axial tilt. We might be able to explain that information by this era of heavy bombardment, right, which introduces a lot of variability, and could explain why we don't see such perfectly orderly motion, but we see exceptions. Okay, so again, this is the same picture from earlier. We've got the 8 planets. You can sort of see tiny little Pluto there at the end. Why did they turn out so differently? Even though they formed from the same materials. So we talked a little bit about where they are with respect to the frost line determines what kind of material will condense there. The more material that's able to condense, the more stuff it'll pull onto it. And that's why the outer planets are so large. More material can condense where it's colder, and that allows it to have a larger gravitational pull, which pulls more matter All right. So on the next slide, we're going to look at the interior of the 5 terrestrial worlds. The 5 terrestrial worlds. Anybody think they know what the 5th terrestrial world is that I'm talking about? Because as far as I know, there are only 4 terrestrial planets.
Are you talking about Pluto?
Nope, Pluto is not a terrestrial planet. Pluto is also not a planet. It's a dwarf planet, which is a separate category of celestial
Well, 15
body.
years ago it was.
Then we updated the definition for what makes something a planet, and Pluto does not fit the bill.
All right, well, let me ask you this. Is the planet you're talking about a gas giant?
No, it's terrestrial. It's rocky. It's big. It's in the inner solar system.
Is it a moon?
It is the moon. All right,
Oh,
we
the
are also
moon.
going we're going to look at the moon's interior as well. So take a look here. I want you to note just the different things that it says here in this slide. I want you to ask questions about things that you don't know. And I want you to note what are some of the differences in the planets, the worlds that you're seeing here in terms of their interior structure.
I think the main difference I see is that Mars and the moon have pretty similar structures in terms of the lithosphere. The lithosphere is a lot larger than most of every other structure. Like
Yeah,
Earth,
they do.
Venus, yeah.
Yeah, they do. The moon and Mars have very large lithospheres. That's true. What else? That's a good observation, Aman. Keep them coming.
Also, Mercury has, in terms of the ratio, has a much bigger core compared to all the other planets.
Absolutely. Absolutely. By percentage by volume, Mercury's core is makes up much larger of a percentage of the planet, for sure. Good observation, Andrea. What else? Do we know what a lithosphere is? Anyone? I'm going to show you a picture in a slide coming up. But the lithosphere is so Earth has different layers, and also depending on how you are categorizing those layers. But like Earth has a crust, Earth has a mantle, Earth has an outer core, Earth has an inner core, right? So that's sort of how you would break it up if you're like describing the layers by composition, right? By what they're made of. But if you're talking about by like physical properties, you'd probably group the crust with part of the upper mantle. And together that makes the lithosphere. So take a look here, I'll show you. I'm going to bounce back and forth between slides for a little bit. And so if you're, again, by chemical composition, you have the crust, which is this little brown bit at the top. You have the mantle, which is this whole like green, tan, orange section. It's made up of silicate materials where the crust is made up of granitic and basaltic rocks. And then you have the core. All right. You have, let's just call it the core, where it's made of iron and nickel and sulfur. Then if we're instead categorizing Earth's layers by its physical properties, then we're going to look at this side. So if we take the top part of the crust, if we take the crust and the top part of the lithosphere, let me start that over. If we take the crust and the top part of the mantle, called the rigid mantle, Together they make the lithosphere. The middle part, the middle layer of the mantle is called the asthenosphere. Right? The asthenosphere is where like convection happens. I don't know how many of you remember from like earth science how we have tectonic plates, right? Show of hands, tectonic plates. We remember what that is?
Yeah.
Okay. Thank you, Andrea. So tectonic plates are like chunks of the lithosphere, right? The lithosphere is like this big jumbled up puzzle piece. And the asthenosphere is a layer in which there's convection, right? And then the convection of the asthenosphere is what moves the tectonic plates around at the surface. Then we have the lower mantle, which is also fairly rigid. And then we get to the core, and there's an outer core and an inner core. So now, instead of just saying, well, what is the core made of? We're looking at the physical properties. The outer core is a liquid layer. The inner core is a rigid, solid layer. It's the solid inner core. And so we sort of go from like solid in the lithosphere to sort of like liquidy, kind of like a molten plastic in the asthenosphere, back to solid in the lower mantle, back to liquid in the outer core, back to solid at the inner core. And it has to do with how pressure increases as you get farther down, and also temperature. So we sort of get like these different phase changes. Even though it's the same material, it takes on different physical properties with depth, which is important to note. So let's look at this slide. Right, this is just looking at the Earth. Okay, so the Earth has the metal core, right, and the core is the most dense part of a planet. The crust is the least dense, right? So there's sort of a density gradient, right? As you go from the surface of a planet to the center of a planet, density goes up. Okay, so let's take a look here. We've got the rigid lithosphere. Remember, these are your tectonic plates. Then you have the rest of the mantle. Somewhere in here is the asthenosphere. Then you have the metal core. The outer part of the metal core is liquid, the inner part is solid. Now let's look back at this slide. All right. On Earth, what are some natural disasters that occur?
Earthquakes.
Tsunamis,
Tsunamis.
volcanic eruptions.
Volcanic eruptions. That's good. Let's keep it with those. Let's stick to those three. What causes all three of those? What causes earthquakes?
Tectonic plates crashing into each other.
Correct. It has to do with tectonic plate activity, right? When plates like grind up against each other and store a lot of energy, and then they like snap and release that energy all at once. You know, when tectonic plates subduct underneath one another, material melts and you get volcanoes forming. Tsunamis happen when earthquakes occur. So tectonic activity, right, is responsible for a lot of natural disasters. It has, and those processes shape Earth's surface, right? Volcanic eruptions build new crust when lava solidifies. Earthquakes can level mountains. Tsunamis can also, contribute a lot to weathering and erosion, reshaping our landscapes. And so in order for that tectonic activity to occur, you need to have the convection of the asthenosphere. Or you have to have that sort of like plasticky part of the mantle that's circulating due to heat from the interior that moves the tectonic plates at the surface. If you look at Mercury, right, we jump right from the lithosphere to the core. notice there is no liquid mantle in there, no plastic mantle. So there's no geologic activity on Mercury. The moon also, the lithosphere is incredibly large, right? The rigid mantle is like the entirety of the mantle is rigid. There is no liquid part to it. So also not really much tectonic activity on the moon. Now, if you look at Mars, Mars has a pretty large lithosphere, but right in there between the lithosphere and the core, there is a layer of mantle that can circulate heat, right? And so there can be some tectonic activity on Mars. But look at Venus and Earth, where there's a lot of liquid mantle in there, right? It's in these planets that you would expect and do see the most amount of tectonic activity. We're going to keep that in mind as we go on to the next couple of slides here. All right. So let's see. So how do we know what Earth's interior even looks like? Because we've never been, I'm going to pull up this slide. I like this one. Like, you can sort of see here, it gives you different depths, right? So like the lithosphere, or rather the upper mantle, the rigid part up here, the green, is 60 miles below the crust. All right. And the asthenosphere, the plastic mantle, is 430 miles below the crust. All right. And the lower mantle is 1,800 miles. So how far do you think we've gone? To which of these layers have humans delved?
I want to say at maximum the asthenosphere.
Okay. How many of you would agree with Ian's conjecture? It says the asthenosphere. James, you agree with that?
Feel like they have gone a little bit lower than that, like
A little
not too
lower.
much. Yeah.
Okay, so maybe you think maybe we made it into this layer here, the orange,
Yeah, but like just like the top of it.
like just up here maybe. Okay. Sorry, James, I saw you turned your mic on.
Yeah, no, I was gonna agree a little bit lower.
So you think a little bit lower also. So you think in like the upper part of the lower mantle.
Correct.
Okay. Andre, what do you think?
We'll be saying the mantle will be saying not to maybe right there, yeah.
Right where I am right here?
Yeah.
Okay. All right.
Well, I think less. I think on
You
the
think-
top. On the top,
Like-
yeah.
Like
No,
up here.
not that one, no. Down a little bit. On the mantle, but just on the top part of the mantle. Yeah.
Like this part?
Yeah.
So I mean, remember, the green, the tan, and the orange are all the mantle.
Okay, so on the orange part, but just right on the border with the plastic one. You said,
Right.
yes.
Okay.
Yeah, it was.
Okay. Andrea, what do you think?
Hi, I have a question, Professor. When you said delved, did you mean like drilled? How far deep they
Just
drilled?
what's the farthest that we've ever gone? Yeah, drilled.
Drilled, I guess.
Gone.
Okay.
Sure. What's the farthest that we've ever drilled?
I think a little bit below the lithosphere, like the greens, like into the asthenosphere, but just like a little bit, not too, like maybe
Into the
200 or
asthenosphere.
something.
Okay. What I'd like for you to do, right, really quickly, everyone, is just quickly Google what's the
Okay.
lowest we've ever been.
Wait, I want to gamble. We haven't even gotten to the lithosphere.
Well, I mean, if you stick your finger in the ground, you dug into the lithosphere.
Oh, so it's like,
I just
I thought there was more to the crust than just, okay.
Well, the crust is part of the lithosphere. That's why That's why that worked. That's why putting your finger in the ground is going into the lithosphere. The crust is part of the lithosphere.
Is
I
it
see.
is it the Kola super deep borehole? It's like the first one that came up.
How deep is it?
40,230 feet deep. So yeah, that's way really
40,230 feet deep. Well, hold on. You're in feet.
feet deep. Yeah.
How many miles is that?
About 8 miles.
It's about 8 miles.
Miles.
8 mile. Eminem would be so proud of
12.2,
us.
yeah.
So, folks, we haven't made it beyond the crust.
Mhm.
We haven't made it below the crust of our planet. Look how thin the crust is compared to everything else. We've never been to the mantle before. We've never been there. We've never dug that deep. So how in the world do we know what the different layers of Earth look like if we've never been there? It's an important question, isn't it? So how do we figure that out? Well, we use earthquakes as probes to figure out what the interior of our planet looks like. So when an earthquake occurs, there are two types of waves that get emitted. They are called P waves, which are primary or pressure waves. And then there are S waves, which are secondary or shear waves. So you can sort of see in the diagram from how this person is holding the spring, the slinky, that the pressure waves, like in both cases, right, whether you're looking at the top image or the bottom image, the wave travels from left to right. In the top image, there are going to be parts of the spring that are compressed and parts that are elongated. Compressed, elongated, so on and so forth. With S waves, the material shakes up and down even though it's traveling from left to right. So the direction it's shaking here is perpendicular to the direction it's traveling. Whereas with P waves, the material shakes parallel to the direction it's traveling. We've got two kinds of waves. Right? Again, we got P waves, primary, S waves, secondary. Primary and secondary also give us a clue as to which one would arrive first, which one travels faster. Primary waves travel faster. Secondary waves do not travel as fast. So why, how do waves help us probe the interior, and why do we care that there are P waves and S waves? Why do we care that there are these two types? So just take a look at this picture for a sec, right? At the top of the Earth, right here, where it says earthquake, you can see that point where all of the different blue and green arrows are originating. P waves and S waves are both capable of traveling through solid materials. But only P waves, only the pressure waves can travel through a liquid also. So when a secondary wave, when an S wave reaches a liquid, it doesn't go through at all. It does not transmit into the liquid. So when an earthquake occurs, right, you got P waves and S waves all being generated at this location due to some tectonic activity. And the P and S waves go in, they curve up, they curve, right? They bend a little bit due to the differences in density and pressure in the material. And going from the earthquake all the way down the side of the Earth to this spot over here, or to this spot over here, you would be able to receive both P and S waves from that earthquake. But once you pass that point, no more S waves as you go to the far side of the Earth. only P waves, and that's only in this purple region. We're going to come back to the blue regions in a second. There's this purple region here where you only get P waves. What that tells scientists is that part of the Earth's interior has to be liquid. All right, if the Earth were solid all the way through, we would get S waves arriving at the other side of the Earth. Since we don't, we've inferred that there is in fact a liquid interior. Well, then how do we know that there's an even smaller solid inner core within that liquid outer core? How do we know that there's a solid inner core buried deep in there? Well, if this layer were entirely liquid, we would be able to predict how the S waves would bend and when they would arrive at certain spots based on how far they are from this earthquake. But they don't bend that way, right? That you like follow my mouse, for example. All right, we're coming down. We hit the outer core, causes our P wave to bend. All right, then it hits the inner core. It bends again, changes the direction. Then it reaches the outer core again, bends, reaches the mantle, bends, reaches the surface. All of these extra bendings increase the time it takes to reach the other side. So we can figure out just how much the bending is being altered and then figure out how large this interior, the solid inner core is. We can figure out its volume, right? And do the same thing for the outer core, figure out how large the outer core is. And the mantle, right? So very, very cool how we can sort of probe the Earth just by keeping track of like these natural events that occur all on their own, right? Right. So again, the important part here is that we are able to determine that we have a molten core. We have a molten core. So far, are there any questions? Oh, just real fast, those blue zones are called shadow zones, right? Remember that the Earth is spherical. So this blue region actually makes a ring around the entire Earth. There is an entire ring where if an earthquake occurred at this spot, you would not know that that earthquake ever happened because you wouldn't feel it at your location on the surface. Any other location could detect this earthquake, but the ones in the shadow zone. Okay, so let's talk about the molten core for a second and why that's important. Right. Earth has a magnetic field. Most of us are aware of that, I imagine. I'm sure you're all familiar with a compass, a magnetic compass, and how a compass works by aligning itself with a magnetic field, right? So you take a compass outside, the needle points north, we're in a magnetic field. Well, why do we have a magnetic field in the first place? How does a planet get a magnetic field? Do all planets have magnetic fields? The answer is no, not all planets have magnetic fields. A magnetic field can be created when charged particles like electrons circulate, when they move in a current pattern. And in the liquid outer core of Earth, we have just the right conditions for the generation of a magnetic field, right? The outer core is made of metal. Metal is a good conductor of electricity. The metal here is molten. It is a liquid metal, so it can circulate. So now we have this metal that is a good conductor of electricity that is circulating, and the electrons in these metals then generate this magnetic field around the Earth. So Earth has a molten iron core, therefore Earth has a magnetic field. Jupiter is a separate story. We're going to talk about the liquid metallic hydrogen core later on, probably next week. Right, and so the presence of a magnetic field indicates the molten core, right? It's sort of the opposite way of thinking about it. Like if we looked at a different planet, if we looked at the moon, for example, and we say, does the moon have a magnetic field? No, it doesn't. Then we could infer that the moon does not have a molten iron core, because if it did, it would have a magnetic field. See how that works? We're using deductive reasoning. All right, so why is Earth's magnetic field, aka the magnetosphere, important to us? Why do we like having a magnetic field? Well, one, we use it for directional stuff, but also it protects us from the solar wind, which is a stream of charged particles that come from the sun, which are highly energetic and can do a lot of damage to anything that they collide with. Right? These charged particles are, in fact, what create the aurora that we see at the north and south poles. So like in the northern hemisphere, you have the aurora borealis, right? And in the southern hemisphere, you have the aurora australis. So how does that work? Well, here's the Earth. You can sort of see it there, that dot in the center. And then there is the magnetic field around the Earth. It's a large magnetic field as far as we can see in this picture, in this depiction. And the solar wind particles, this stream comes in nearly parallel. But when the stream gets close to the magnetic fields, it gets deflected. And some of those solar wind particles go around the Earth and past it, right, which protects us. And then some of the solar wind particles get redirected along the magnetic field and actually make their way to the top and bottom of the Earth, or I should say to the north and south poles of the Earth, where they interact with the atmosphere, right? These solar wind particles strike the atmosphere, causing energy level transitions, which give us the aurora. And so here are 3 more pictures. The different colors that we see in the aurora have to do with the atoms in the atmosphere, right? So we talked last week about light and how every element has its own unique emission spectra, right? Light, the colors that get emitted by that element. And some of them are more intense than others, right? Some, like within a particular atom, you know, a certain band of color might have higher intensity than another. And so we can see here that, you know, oxygen has different energy level transitions, which correspond to both red and green light. So this is due to it hitting oxygen. You know, then you might look at some of these colors and say, well, this is because the solar wind is hitting the nitrogen in the atmosphere or something like that, so on and so forth. Right? And so that's why we get these stream of charged particles. Very cool. Has anybody ever been to Iceland or somewhere where you can see the northern lights?
Yeah, I
I
was in
wish.
Iceland just 2 years ago.
I wish too, Andrea. You were there, Ian? Did you actually get to see the lights?
I wish, I really wish I
Yeah.
could have seen the aurora borealis. However, though, I have been to Iceland. I mean, like I have been out at night, so I have like started to see at least some, I guess some color in the sky, but not the actual aurora.
So
I'm
what
really
time of
curious
year
for
did you
that.
go? What time
Huh?
of year were you there? What time of year were you there?
I was there in February.
So you're there kind of like towards the end of the season,
Yeah.
right? So the best time to go is in like the winter months, like going from like, I guess like November or so to February, when the sky is dark for long hours of the day, right? And then you have a really good chance of seeing the aurora. Okay, very cool. Yeah, I'm hoping to go there also one day.
You honestly should. It is probably one of the best places on earth you could go to. In a
Oh
way,
yeah, I know, it's incredibly beautiful there.
yeah, it's like imagine Hawaii, but it's in, it's on an
in the north.
island in
It's not
Northern Europe.
tropical. It's the non-tropical Hawaii.
Yes,
Okay.
and it's incredibly beautiful.
So there's the plug, everybody. Go to Iceland. So how do we probe the interior of the Earth? We look at seismic waves, right? We use seismic waves to measure and infer information about Earth's interior, right? And the planetary and magnetic fields are caused by that dynamic molten metal, right? We call it magnetic dynamo, which is the circulation of molten metal, which causes a magnetic field, right? So this can only happen, again, if the interior is hot. And that brings me to this next all-important statement. This is an incredibly important theme of astronomy. Right, there are first, I'm gonna get there. There are three sources of internal heat, okay? One, gravitational potential energy of accreting planetesimals. So when a planet's forming, back in the day, right, during the early stages of the solar system's development, when the planets formed, you had all of these planetesimals colliding. All of that gravitational potential energy that they have as they collide gets converted into kinetic energy, and then they smack into each other and it forms heat. That heat is stored in the interior of the planet, but it's slowly being released over time. Then there's another process of differentiation. Notice when we pulled up the layers of the 5 terrestrial worlds, they had distinctly different layers. There was a crust, there was a mantle, there was a core. You don't really see that differentiation in other objects like comets and certain kinds of asteroids. But differentiation is due to the fact that when the planet formed, it was so hot that it was basically a giant molten ball of liquid material. And the more dense materials could sink to the center, which pushed the less dense materials up to the surface. In that process, you have material sliding past other material, and that causes friction, which generates internal heat. The Earth no longer experiences these two as ongoing sources. However, radioactivity is an ongoing process that keeps Earth's interior warm. There are radioactive elements within the Earth that, as they decay into more stable elements, they release thermal energy. And so that is the process by which Earth's interior is kept warm currently. This is the important point, that heat drives geological activity. Without heat, you don't have tectonic plate activity, right? So you wouldn't have volcanoes, you wouldn't have quakes, you wouldn't have tsunamis. But heat is also what allows the the molten, it's what allows for a molten outer core of metal, which allows us to have an atmosphere, right? Without the atmosphere, we wouldn't have weathering and erosion. We wouldn't have weather on the surface. There would be no rain because we wouldn't have an atmosphere in which rain can precipitate. It would be a lot colder at the surface because the atmosphere is what traps heat. So that kind of gets us into the conversation about greenhouse gases. So without heat, there is no geological activity, right? There are no surface processes. So here's a thought question. Which cools off faster? I'm going to change the options here. A large cup full of hot coffee or a teaspoon of hot coffee in the same cup? Which cools off faster?
B, but I feel like this is a tricky question.
Why do you think that? What do you think is tricky about it, Jurian?
Because it's, obviously you're gonna think it's a teaspoon because, it's small. But then what if it's the large cup full of hot coffee? I don't know. It's tricky.
So you think I'm trying to pull like a gotcha
Yeah, yes.
on there? I am not. I am going for the blatantly obvious, right? It is the teaspoon. Right? The teaspoon is going to cool off more quickly than a full cup because there's just less stuff to cool off. But the reason I'm asking that is to prime you for this question. Which cools off faster, the big terrestrial planet or the tiny terrestrial planet? And now we should all be thinking the same thing, which is tiny terrestrial planet. There's something that is smaller is going to cool off faster. So, there are three processes by which heat leaves a planet. One is convection. So, in the mantle, in the asthenosphere, that plastic mantle layer, you have heat from the core touches the bottom of the mantle. It's almost like a lava lamp, okay, inside the mantle here, where hot rock will expand and rise, and then it'll transfer some of its heat to the crust through conduction, right, where it's making contact. And then that heat will radiate outward into space in the form of radiation. Right, so convection, conduction, radiation. All right. When we look at the other planets in our solar system, I'm going to pull up the map again of the 5 terrestrial worlds, and we're going to look at the role of size. Right, how size plays an important factor in determining whether or not they are geologically active. Right, so looking here, right, the smaller worlds cool off faster. The moon, Mercury, Mars cool off faster, causing them to harden. Mercury and the moon have no liquid, they have no asthenosphere. So there's no tectonic activity. Mars has hardly any asthenosphere. So there's very little tectonic plate activity. Now, if the interior were hotter, right, if these objects had more heat, then there would be a molten layer here, and there would be tectonic activity or geological activity. But because they cool down and harden and solidify, no longer are they geologically active. The Earth and Venus, however, are geologically active because they do have these, they do have much more heat in their interiors. So let's move on now to the next bit. Right. Just to add a final thought there, because the moon and Mercury don't have any asthenosphere at all, right? We go straight from the lithosphere to the core. They are considered geologically dead. There's no geological activity. Mars still has a little bit. So there are a couple of geological processes that we need to know about. One of them is impact cratering, which is the process of creating craters on the surface of a planet due to collisions with asteroids and comets, right? So think back to like that era of heavy bombardment that we talked about at the very beginning, right? When we had like all the early protoplanets and planetesimals floating about. Lots of impact cratering. Then there's the process of volcanism, right? The eruption of molten rock onto the surface. which is closely tied to tectonic plate activity, which will cause earthquakes and whatnot. But then there are also other processes like erosion, right, which has to do with the atmosphere and Earth's hydrosphere. So all of these different processes. So when we look at, let me just see what I have on my next slide here. So when we look at these different geological processes, or rather when we look at an object in the sky, like the moon, for example, we see that the moon has a lot of impact craters on it. And so does Mercury. Well, what does that tell us about the planets, or the worlds, I should say, because the moon's not a planet? What does that tell us about these worlds? Well, the fact that they have so many craters has to be somewhat significant. Now, the Earth has been around for just as long as the moon has, if not longer. And it's been around just as long as Mercury or Mars or Venus, right? The solar system all formed at the same time. So why would the Earth have so few impact craters while other objects like Mercury and the moon have tons of impact craters? Well, what do we think, Angelina?
Is it because like more people, they live on Earth, and like the Earth just radiates more heat than the other planets?
Nope, it has nothing to do with, I mean, humans have only been around for a very, very short time in terms of the Earth's history. In the timeline of the Earth, like if you took it and compressed the well, we haven't been around that long, right? But even then, that doesn't explain why we don't really have many craters. It's not like having people on Earth prevents asteroids from hitting the Earth, right? If an asteroid's on its way to the Earth, it's going to hit the Earth. So why does Earth have fewer impact craters? Was it hit by fewer objects? Would that make sense? Or is there something else going on? Well, what are some things that happen? So volcanism, for example, right? Volcanic activity. How does that change Earth's surface?
It can often make like new islands or like build like not hills, but like certain terrains and terraforms and certain terrains and stuff.
Totally, it changes the terrain. Can plate tectonics do the same thing?
As well, sometimes, yeah.
Yeah, absolutely. Plate tectonics, that's why we have mountains, right? In the middle of the Atlantic Ocean, there's a ridge at which two tectonic plates are separating and new crust is constantly being formed. And old crust sinks back into the mantle and gets recycled. So the reason that Earth doesn't have as many impact craters as Mercury or the moon is not that we were hit by fewer asteroids and comets, but rather that Earth is undergoing a continuous process of reshaping itself or fixing up or cleaning up its blemishes, whereas Mercury and the moon can't do that. They can't get rid of their impact craters. Why? Because they're geologically dead, right? They don't have the necessary heat to allow for geological activity that would allow them to reshape their surfaces. Are we starting to see how these things all tie together? Right, you could probably make like a bit of like a conceptual mapping of like, how all these things fit together pretty nicely. Let's move on. So to summarize what we have learned, why is Earth geologically active? Well, it's because it still has a lot of its heat from its formation. and because it's large. So there's more heat to hold on to. Right? What are some of the processes that shape Earth's surface? Well, there's impact cratering, volcanism, tectonics, and erosion. Impact cratering still happens, not as often as it did during the era of heavy bombardment, but things still fall to Earth from space, right? They're not necessarily huge, but things still strike Earth's surface. Volcanoes are always happening. Tectonic plates are always moving. And we have an atmosphere which allows for, rain and just liquid water in general. It allows for wind, and all of these things erode the surface, and material gets transported around and broken down and transported and deposited. So all of these things continuously shape Earth's surface. And with that, I think instead of instead of going on here, I'm actually going to pause. All right, and this is where we're going to stop for tonight. All right, so I'm going to stop my share. If anybody has any questions, I am happy to take them. Otherwise, you can all head out.
I have one.
Sure.
I emailed you twice, and I don't know if you've seen it. I don't know if it's the right email. But if I did send the right email, can you email me back on it, please?
Yep, I'll respond right now.
Thank you.
You're welcome. Any other questions, folks?
Yeah, Professor.
Yeah.
I don't know if it was the lab or it was the one that we had like the simulation and
the lab.
Yeah, and we had to do what was it, the force, but it only let me go to 7 as the maximum, and the question asked you to do 8, but it didn't let me go any further.
You're talking about the simulation with the Earth and the Moon and the Sun?
No, the one that was I think I took a picture of it. Hold on.
Okay.
Yeah, it was force on mass.
Oh, okay. All right. Yeah. With the two with like it's the one with the equation FG equals GM1M2 over R squared.
Yeah, and it lets you pick the mass 1 and 2, like the billion kg.
Okay. All right. So you sent me an email, you said?
No, should I?
Send me an email with the picture and just ask for me to adjust the points for you.
Okay. All right. Thanks.
All right. If it's saying to put it to a setting, just like show me that when you can't reach that setting. Show me that you've like reached the end of the bar.
Right.
You know what I mean? Okay.
Okay. Thank you.
Great. You're welcome.
Right. Hi, Professor.
Hi, Andrea.
I have a question about the sign up for the space mission assignments.
Yes.
Where were we supposed to sign up? Because I checked on Blackboard, I couldn't find any place. Was it through our school email? Because I don't have access to that right now. I have to work with that.
It's on Blackboard. There's a link to a Google document.
Okay, I'm gonna look again. All right.
If you look in the announcements section, you should be able to see the link in the announcement.
I actually saw like the discussions, like for me, like in the in that area, right? I only saw like the discussion for week 2 and 3. I don't know why it says it's overdue, because I did do those discussions too. And I'm not able to scroll down on my computer for some reason. I've tried many different times, so I never saw anything in that area for like a Google link or something.
Okay, can you click on, are you on Blackboard right now?
Yes, I think so. Let me just go back onto it.
All right, I'm also going to stop the recording. So to anybody that's watching, thank you for watching and take care.